Okay. So today we continue, we come back and look again a little bit better at the issue of multi-thread and parallelism with C++. So I'm coming back to the slides I've already shown, and I added a little bit more, and I made them a little bit more precise. So concurrency in C++, we have already seen how to create a thread. So basically, you just have to create an object of a class thread by passing a function. And once you have a function, you can just... So actually, this code is the only one I did not correct. So sorry, I'm just going to correct it right now. 1 second. Sorry about that. I just forget the only piece of code I should have corrected already. Okay, so basically you have one function which is the body of your thread, the one that is going to be executed, and then later on you can define an object of type thread, and then you can create the thread, and once you create the object, the thread starts executing right away. And then later on you can join the thread. Threads object cannot be copied, okay, but they can be moved, so you can basically return them from some function. To create a thread, you have to pass anything that can be called, so what is called a callable, so for example a function object, and then you can do something like this. You create an object x, and then you return like this. And this is perfectly legal even if x is destroyed, because by doing invoking this constructor, x is copied into the internal internal implementation of the thread. So even if this x is destroyed, it doesn't matter, because at the point in which this constructor is called, the object x has been copied. However, if you want to pass a reference, you do like that, but then you have a problem, because when you destroy x, the reference to x is not valid anymore, and so the thread is going to do something very bad or very stupid. So you have to be careful about this. So C++ is a typed language, as you know, but you can do very bad things with memory. So you have to be careful how memory is handled, and you have to know these details. Am I going to copy the object or not? In this case, the object is copied. In this case, it's not copied because of this call to standard reference that transforms this object x into a reference. And so the thread is going to be created containing internally appointed to a reference. As you know, actually thread is a template constructor. So basically what happens is that internally it's going to store a reference and not an object. Arguments are copied too, so unless they are references, it's okay to destroy them afterwards. So basically you can do like this, and everything is going to be okay because you have an object, and this object is copied into the thread and is passed to my function as a reference. If you really want to pass a reference, as always, you have to use a standard reference. Okay. If a function or callable object that is passed to a thread throws an exception, the program is terminated. So for example, suppose you have this F here, which is the thread body, and this F is passed to the object myth, and then I want to join end-to-end. So if I look at the main, everything is going to be okay. But actually, F prints something on the screen, then sleeps for some time, 1 second, and then throws an exception. So what happens is actually that the entire program is aborted because the function throws an exception that is not catched by anybody, and so the program is aborted. So I'm going to use Emacs today as editor. Okay, can you see? I hope you can see. Can you see?
Yes. Yeah, okay.
Okay, so waiting for something to happen. And then it prints this is a thread, and then terminate called after throwing an instance of char const abort the call jumped. So this exception was thrown, but nobody was able to catch it, and so the program aborted. And of course, I cannot catch that in the main. Exception can only be forwarded and catched within a thread. So I can write a try here to catch the exception. Okay, but of course I cannot write anything in the main because I don't know where to write it actually. So the exception is forwarded and goes up, but only within a thread. So when it reaches the last level of function call of a thread, is going to abort. In this case, of course, is not going to abort because I'm catching it. Okay, so catched. This will not be printed. Actually, this is printed because now we catch the exception and ending. So exception must be catched within a thread. What happens when you destroy a thread before it has been terminated? So if you destroy the object, here we have a body, and again this prints this is a thread and sleeps for 1 second, and then it asks himself it's still alive after 1 second. And in make thread you create an object myThread by passing body, and then you return. Now this myThread is a local object on the stack of this function myThread. So what happens is that this object is going to be destroyed when the function terminates. Okay. So what happens is that oh, sorry, actually I think I changed the program. So if I don't do this, so this is now is exactly equal to the what I find on the slide. So you have an abort immediately because you destroy the object. So the object is destroyed and the thread has no object to refer to, and so there is immediately a core dump, an abortion. So you cannot do this. If you want to avoid this, because for some reason you don't want to wait for the object to terminate. So if you really want to achieve this, what you can do is to detach a thread. Detaching a thread means I don't want to any relationship to the executing thread and the object. So when I do my thread detach, this object is not responsible anymore for the thread, and so it can be destroyed safely without anything happening to the thread. So if I do this and I recompile, now I don't have the error anymore. This is a thread. Am I still alive? Yes, of course. Okay, so we have that if an object is destroyed before the thread has terminated, then we have an error and the program aborts. If instead you want to achieve this behavior because you don't care about joining a thread, then you have to detach the thread. So the abort is triggered by the fact that every thread in general must be joined by default. If we lose the reference to the thread, we cannot join the thread anymore, and so this is an error, and this is going to abort. Instead, if we need this, we need to forget about joining a thread. We want to just leave it free to execute as long as it care, as it want. Then you have to detach the thread. This means that the thread continues execution, but not possible to join it anymore. So you detach it, and the object itself becomes not a thread. And if you want to join a not a thread object, the join returns immediately without any particular error. So again, if you destroy the object before the thread terminates, like in this case, then you have an abort. If you want to forget about the thread, you call detach. Another thing interesting is the thread local variables. Thread local variables are global variables that are specific to each thread. So basically, a thread local variable is specified like this. So it's like a specification like static or like external, things like that. You can also specify thread local. And what it means is that every time you create a new thread, a copy of this variable is created in memory for that thread. So when you write thread local int index, there are going to be many index variables, one per each thread. Of course, these are local variables to each thread. So one thread can only access his own copy, cannot access somebody else's copy. Okay? Unless, of course, you use some sort of inter-thread communication mechanism. But directly, you cannot access but your own variable. So, for example, here I have a function body, which is passed the parameter x, and sets index equal to x, and then prints my index is index. And then later on, you print index. Now, which value is going to be called? Well, that depends on which thread calls this function. Okay? And what is the value of index for that thread? It can be different for every thread. So let's make a very, very simple example. Okay, I will write it from scratch. So let's see at one way of creating many threads that looks a lot like so we are going to create 5 threads. So for creating 5 threads, I'm going to use one function that is transform from the either algorithm, and I'm probably going to use also function. So I have a vector of integers, and I want to obtain a vector of threads by creating these threads. So for every thread for every index in a vector index, I produce something that I'm going to insert into vector th, and what I produce is given by this function. Okay, so what I'm going to do is to create, this is a lambda function, which is passed an integer and creates a thread that has as a main function body, and is passed the variable x. And variable x, of course, is going to be 1, 2, 3, 4, 5. Okay? And then I want to join all of them. So I'm going to do for each th.begin, th.end. So for all elements inside th, I'm going to execute this function. So for each thread inside here, I'm going to call the join on it. Okay? I hope it works at the first try. So this is called thread local. I'm going to put that into Makefile. Okay, I think I made an error. What? Okay, so first of all, I forget to say that index is an integer. That makes sense. Then another error. So again, index function is not. So I think the other errors derive from there. Let's see. And there is some more error. Okay, function is not a good name for a function. Let's call it f. Because of course inside functional we have an object that is called function. So. And the last but not least, okay, and this is vector of threads. I forget a semicolon here. Okay, so the printing is not very ordered, but we have thread started. Then the thread 2 and 5 have been started, and thread 1 has started. And finally thread 3. So 1, 2, 3, 4, 5 have started. Then in the number 4 prints that index is 4. Then here we have a lot of very strange printings, not very well done. And let's see if we can simplify this a little bit. For example, by executing this into mutex. Now the function is executed in mutual exclusion between all the different threads. So at least the printing of the index is done in a certain order. This one not, but it's okay. Hopefully we will understand what's going on. Okay, so everybody prints his own index. So this means that variable index is not a global unique variable for everybody, but is a variable that everybody has his own local variable. Okay, so writing index here does not assign to a single place in memory, but every thread is going to have its own place in memory. Okay, so mutual exclusion. We have already seen last time mutual exclusion. Let's have a little bit of summary of what we have seen last time. So we have different kinds of mutex. They can be simple, recursive, or shared. And each one can be timed or not. Usually you can lock a mutex directly, for example, by using lock and unlock directly on the music, or you can use one of the guards like unique lock that we have seen before. So let's try first to see this lock and unlock. You can actually also use try lock. That means you try to lock, but if it is not possible, then you return with an error. At timed music also supports try lock for and try lock until. Try lock for means you try the lock for a certain amount of time, like for 2 seconds. Afterwards, you finish. And this one instead means you try the lock until a certain absolute point in time. For example, exactly at that instant, starting from the original epoch. Okay, so the first one takes an interval of time, and the second one takes an absolute point in time in the future. Shared mutex also support lock shared, that is for the reader-writer mechanism. Shared mutex are actually not still available on GCC because they will be available only from the next standard, which is C++ 14. So we have to wait a little bit before we can get shared mutex into the C++ standard. This is an example of recursive mutex. So the idea is that you have a recursive function, which is passed as an integer, and this can be called by several threads at the same time, so you need to be exclusive between threads. But since it's recursive, you can lock this mutex many times. So if it is the same thread that locks again, then it doesn't matter. Then there is no problem because recursive mutex doesn't lock the same mutex twice from the same thread. So basically, if you call recursive function, this is the first time is going to lock this mutex, then increment some global variable, and then calls this recursive function by passing x decrement by 1. So the next time recursive function is executed, it will try to lock again this recursive mutex, but since this thread already locked it, then nothing happens and continues to execute. So I have the example here. Let's see, where is it? I don't remember. Yes, here is it. So basically you have a recursive function, and we are going to call it in the main like this. So we make a thread which calls body, which body is going to call a recursive function. Okay? So again, let's concentrate on the recursive function, and let's see how it executes. Okay, so created, I am the thread. It's called with 4. Then this is a recursive function 4, 3, 2, 1, and no recursion, and that's it. Of course, if you change this to a standard mutex, you go into deadlock. This is a recursive function. It's called the first time, and then it blocks forever because it's trying to lock twice the same mutex. So it must be a recursive mutex. And of course, this is more useful when you have things like a class. And for example, suppose we have this class shared that defines internally a recursive mutex and two functions f and g. And f just prints inside function f, and g prints inside function g and calls f. And they both are executed in mutual exclusion using a recursive mutex. So basically, this time we have another function which I call object thread that is passed its own index and a reference to a shared object, and it calls G on this shared object. So in the main now I create two threads that execute this function object thread with two indexes and a reference to a single shared object. Remember that you have to create a reference, otherwise two objects are going to be passed and copied. Okay? And actually this class is not copyable. I just deleted the copy operator and assignment operator, so you cannot copy an object of this class. So you are forced anyway to pass a reference. So the second part is going to tell you that thread 1 inside function g, inside function f, thread 1 terminated, and then thread 2 inside function g, f, and thread 2 terminated. So the two threads do not overlap to each other because of the mutual exclusion, and there is no deadlock because of the recursive mutex. So we can also try to remove this reference. So I will show you that actually the compiler will catch this error. in a very bad way because the error is almost unreadable. But basically the thing is that you cannot copy shared. Okay, and here I'm trying to copy shared, so that's not possible. So the second way to access mutex, as we've seen already, is using guards. So basically, we are going to use the so-called RAI technique. And the simplest object for a RAI technique is lock guard. So basically, you define an object L of type lock guard by passing a mutex. And this is the critical section of code, and if an exception is thrown here, this mutex is automatically released. So this is the advantage of using a lock guard. And then we have a unique lock that it also allows you to unlock and lock directly using these functions. So instead of doing mutex lock and mutex unlock, you can do L unlock and L lock. Okay? So it's a little bit more complicated than lock guard. There are also global functions for locking and unlocking, and these can be used when you have to unlock several mutex at once. Suppose, for example, you have a structured bank account, and this bank account has a variable balance, and to do operation on this balance, you have to lock a mutex before. Okay? And suppose you have to do a transfer from a bank account from to a bank account to of a certain amount. Basically, what you have to do is to lock both from and to. And to avoid deadlock, it's better to lock them at the same time. So by doing a standard lock, it tries to lock at the same time the two. If it's possible, then okay, both are locked in an atomic way. If this is not possible, none of them is locked. But it's never the case that one is locked and the other is not, and or vice versa. Okay? So this locking operation you can see as an atomic lock of two mutex, and they can also be more than that. So you can put as many parameters as you want here. So basically, lock is implemented using variadic templates. Okay? So lock allows you to lock several mutex at the same time, and unlock does the same. Allows you to unlock several mutex at the same time. Okay, but this does not use guards, so you are responsible for unlocking that. So how can I combine the power of locking multiple mutex at the same time with guards? Well, you can do by using this piece of code. Basically, when defining a guard, sorry, I closed the window because there is a little bit too much noise. You can use this technique. So when creating a guard, you can pass an additional parameter that can be defer lock T, try lock T, or adopt lock T. Defer lock T means actually don't lock the mutex. So you are the guard that takes care of the mutex, but you are not going to lock it. I will lock it later explicitly. Or try to lock it, tries without locking. Or you can specify adopt lock, adopt an already locked mutex. So basically, you can lock both mutex at the same time here, and then adopt the two mutex with these two objects. And if this is successful, and it is successful because they are both locked, then you can execute your code, and when the function finishes, these two will be released and will unlock the mutex. Okay, so you combine the global lock with multiple mutex with guards that are very useful because allow us to automatically release when we go out of the function. Another nice thing that can be done is to execute some code only once. For example, look at this. We are going to define a flag of type once flag, then a function do once that will call a certain function here defined as one single lambda function, and it will call this function only once. So when I create three threads here, and these three threads execute all of them the same code, actually what happens is that this is going to execute only once, exactly what we mean by call once. So, as I said, thanks to this flag and thanks to this API, we can call one certain function just once. Okay, so now we look at condition variables, and then we do a few exercises on using condition variables in C++. So condition variables are used when we want to block a thread on some condition, so basically to synchronize threads. And as you know from the operating system course, condition variables should always be paired with one mutex, so they can realize what is generally called as a monitor. Okay, so you have a mutex which guards a critical section, and inside the critical section you can block on a condition variable. So the interface today is very difficult. Huh? So the interface is that you have one default constructor, and usually these condition variables cannot be copied or moved. Okay, so you cannot configure like this. And then you have function wait that takes a unique clock while the thread is. So you will write a function like this: standard unique lock L, which takes a mutex M, and then while condition CV wait L, where condition is some Boolean condition that has to do with your code. Okay. Very nice. Sorry, guys. Okay. Okay, so other parts of the interface. So guys, we do a break now, and let's hope that they finish to make holes in my head for a while. Okay, so we do a break of 10 minutes.
Okay.
Okay.
What?
Yeah, come.
Those, yeah.
Yeah. 30 seconds.
Okay. If everybody is back, we continue.
Yes.
Okay. Let's hope that it will last for some time. Okay. So can you see clearly the code?
Yeah.
Here I'm showing an example of a very straightforward implementation of mailbox for passing data through between two threads. So basically the idea is that mailbox is just a vector of data, and I'm using these three variables: head, tail, and n to control the content of the mailbox. In particular, head is pointing to the first free position in the vector. And tail corresponds to the first element that must be extracted. So this is mailbox is actually a FIFO queue of integers. Okay, so head points to the first free element in the vector. Tail points to the first element that must be extracted. N is the number of elements that are not actually contained into the queue, and n max is the maximum number of elements in the mailbox. So when I initialize the mailbox, I have to pass the number of elements, so the number of places in the mailbox. So I initialize v by passing number of places. Head and tail, they both point to 0, and so also n. So initially, everything is 0 because there are no elements inside the mailbox, and so the queue index that both point at 0. And n max point, it's equal to number of places. I disallow copying and assignment of this mailbox, so this cannot be copied. Also because all these three objects cannot be copied directly. So anyway, the safest thing for the moment is just to disable copying and assignment. And the two functions I'm going to implement are put for putting an element inside the mailbox, and get for extracting an element from the mailbox. Okay? And then maybe I may want to implement also something like is empty to understand if the queue is empty. Let's write like this right now. Okay, so mailbox put, I want to insert an element in the queue. So what I do is that I first take a look on the mutex. If everything goes okay, I'm going to check if n is equal to n max. If this is the case, it means there is no more space into the queue, because the number of elements is equal to the maximum number of places. So in that case, I wait on a condition variable that I call full. Okay? When I finish waiting, it means that this condition is not true anymore. So n must be less than n max. In that case, I put x into the vector at position head. I increase n, I increase head, and the head is increased modulo n max. And then I notify somebody that may be waiting because the queue was empty at the beginning. It may happen that I'm inserting this for the first time and somebody was waiting for some element to be inserted into the mailbox. And get is basically symmetric. So I take the lock on the mutex, I check if n is 0, the queue is empty, so I block on the condition empty. When I unblock, it means somebody has put something in the queue. Basically, somebody has called put, and the notify of empty has unblocked me from the here. And so I take the value stored into the tail, I increase tail, I reduce n, and maybe by doing so I'm freeing one more space into the queue. So I notify somebody that could be blocked on full, waiting for a free space into the queue. Okay? And of course I return the value I just read. So this is quite straightforward. What I mean is to implement this is empty. So this is quite simple. So in your opinion, should I put the same should I lock the mutex or not? Do you have any idea if I should lock the mutex or not here?
It's not necessary.
It's probably not necessary because n is an integer, and so the reading should be atomic. We are not completely sure about that, however, but it should be atomic. And so after all, it's not so important because it's empty. It's just a read-only operation. So anyway, it's not very important. Okay, so yes, I'm going to do this. N should be atomic, so you cannot read alpha of n, and so this should be okay. Okay, so now let's write a function for producing. So this should be a producer. Okay, so this produces 50 integers and wants to insert them into the queue. Sorry, mbox.put. Okay, so this does a for cycle and calls this put 50 times. And then let's write a consumer. So the consumer will never stop. Forever, we try to get elements from the queue. Okay, and finally, in the main, I create one producer. So I first declare a mailbox with 4 elements inside. Then I create a producer passing my mailbox as a reference. Then I create a consumer, again passing the mailbox as a reference. And then I detach the consumer because this will never end, so I'm not going to join it, and I wait for the producer to complete. And then I complete the main program. When the main program exits, the whole program terminates, so the consumer will also terminate. So cout and end L, because I forget the include IOStream. And this is the class mailbox. And here I have a using namespace, so that should be okay. Okay, so it's so fast that you don't see anything actually, but it works. So let's actually print something when we produce. And okay, so you see that they alternate, and actually more or less it's in groups of 4, because the producer insert 4 elements, then it's completely full, then the consumer extracts a few, in this case a little bit more than because there was another one before, and then the producer continues to inserting, and so on and so forth. Okay, so this works. So a few notes. So you have seen how we use the condition variable. So basically we do while a certain condition holds, we have to wait. Can we transform this into a if? Well, unfortunately not, because there is one problem that is called spurious wake-ups. So for several reasons, it may happen that the thread is unblocked from the condition variable without any other thread calling notify. For example, it may happen that the program receives a signal, and if it receives a signal, that thread that is blocked may be unblocked from the wait. So the wait may actually return and unblock even when nobody calls the notify. This phenomenon is called the spurious wake-ups. There is another more serious concern. That is, suppose you have multiple producers and multiple consumers. Okay, so if you have multiple producers and multiple consumers that they only insist on the same mailbox, what can happen is something actually a little bit strange. So suppose, for example, that you have several producers, okay, and one producer is blocked here because the mailbox is full. Okay. Suppose that while this is blocked here, a consumer arrives and locks the mutex. So the consumer is in this point of execution. Okay. suppose you have this strange situation. So one producer blocked here into full weight. One consumer arrives and locks this mutex and is arrived here. At the same time, another producer arrives and wants to lock the mutex. But of course, it cannot lock the mutex because the mutex has already been locked by the consumer, right? So the first producer, which we call P1, is blocked here. The second producer is locked here. Okay? Okay, so the consumer continues to execute. Of course, the queue is not empty, it's full, because otherwise we will not have P1 blocked here. So it does what it has to do. So empts, so removes one element. So it produces one free place and notifies this. Okay. However, notice that the lock has not yet been released because I'm still inside mailbox get. So I notify the blocked thread, but I have not released the lock yet. The lock is going to be released later when I go out of mailbox. So P1 was blocked on the condition, now wakes up from the condition, but it still needs to take the mutex. So it blocks on the mutex now. And also P2 is blocked on the mutex. So now we have, so the consumer is at this point, has just finished the notifying. Okay, so this is the consumer. And up here we have the two producers. And they are both blocked on the mutex. Now the consumer returns from the get. So the guard is destroyed and the mutex is unlocked. So one of these two threads must be unblocked. Which one is going to be unblocked? Well, we don't know actually, because it really depends on the operating system implementation. But there is a non-null probability that P2 is going to be unblocked. Okay, so if P2 is unblocked, he moves from here, enters here, he finds that n is just less than n max, and proceeds executing. So now P2 is here. And it executes inside, increments n, putting n again equal to n max, and notifies empty, nobody is blocked on empty, and finally goes out of this function and releases the lock on the mutex. So now the situation is that P1 is unblocked, and if you have a while, you will check again for the condition and will block again, and at least we don't have problems. But if there is an if, when it unblocks from the mutex, we will continue and will overwrite some data and bring n greater than n max, and this is an error. So was it clear? Did you understand? Too complicated? So it's a race. So even if you have mutex and conditions, you still have a race. And the race is that the first P1 blocks here. Then C1 enters and starts executing. And here. While C1 is there, P2 arrives and blocks on the mutex. Okay? C1 executes here, removes something, and notifies. So C1 notifies. C1 notifies means that somebody is going to be unblocked from the condition variable. And who is blocked on the condition variable is P1. So P1 unblocks from the condition variables. But it blocks on the mutex because the mutex is still locked by C1. Okay? Then C1 continues executing and finally unlocks the mutex here. Now there are two threads blocked on the mutex, P2 and P1. And depending on the implementation, it may happen that P2 is unblocked. Now, if P2 is unblocked, it is unblocked from this point. So it checks this if condition. And if this condition is not verified, so it continues executing. And puts something on the mailbox. And in particular, P2 increases n. Okay? So now n is again equal to n max. Now finally, P2 completes, exits. Sorry?
No.
So P2 unlocks the mutex. And finally, P1 is unblocked. Now P1 is unblocked, and what does it do is continue executing. And in particular, P1 overwrites. Okay? So this is an error. And it happens because P2 basically passed ahead of P1. Okay? Now to avoid this, to avoid all this problem, we can just put a while here. So at least when P2 is unlocked from the mutex, it will go back and check again if n is equal to n max. And since this is the case, it will block again. And so we don't have corruption and inconsistency in the data structure. Okay? And let's see what happens when I have many producers and many consumers then.
It's possible notify after the unlock.
Yes, it is, but you are not sure what is going to happen. So even if you notify after the unlock, you are not completely sure that the effect is what you expect. How do you do that? Of course, you can unlock it and then notify. Yes, you can do, but nothing really changes for this problem, because um, um, yeah, because the P2. So let's do this here. The P2 that was locked here, when you do unlock, is going to unblock. But you are not sure that it's going to execute immediately and block immediately on the condition variable. It could remain somewhere here.
Okay.
Okay, while P1 is still blocked here. Okay, so basically C1 has unlocked P2, has not unlocked yet P1, and P2 has already taken the mutex.
Okay.
So it's already inside. So when you notify now in the get, when you notify in the get, you unblock P1, which is going to block immediately on the mutex.
Yeah.
So by changing the order of the notify and unlock, nothing really changes for the program. So there is no easy way out. The only way out is to have a while.
Okay.
Okay, so it's very fast, so you don't see anything, but everything is how it should be. Okay, so another nice thing I would like to show you is how to write a synchronization barrier and how to write a thread group class. So thread group can be useful for parallelization. So we are going to write the third exercise actually. Okay, so how to write a thread group class. So rather than a thread group, what I would like to do is a sort of synchronization class for acting as a sort of controllable synchronization barrier. You will understand what I mean in a little while, I hope. So very often, when writing programs, you need to execute several threads in parallel on a separate amount of data. So what happens is that every thread works on a bunch of data and produces a result. And then after every thread has completed this work, we collect all the results, we put them together, and maybe we have a second round of computation in which we again activate all threads. Everybody works in his own portion of data. We wait for them to complete, and then we start again. We could every time activate and create new threads for doing this, but it's a little bit too heavy because creating a thread takes actually overhead. So another more efficient way of doing this is to have the threads already created but all of them are blocked on some condition, and only when I say start, all of them start, and each one will work on his own portion of data. And when they finish, they block again, and I wait for all of them to block, so I can collect the results and continue the execution in some way. Okay. So one example of this is this exercise. So suppose, so this is a very stupid exercise, but it's just to give you an idea of parallel programming sometimes. So suppose you have a vector of doubles, okay? And you want to iteratively compute this formula in which the element at a certain position I, just see if I can put it larger. So you have a vector, and you want to compute this formula. At step t plus 1, the xi is equal to twice xi plus xi minus 1 plus xi plus 1 divided by 4. So for example, x1 is equal to twice x1 plus x0 plus x2 divided by 4. And that is going to be the next value of x1. And the same for x2, and the same for x3, x4, x5, x6, x7. So doing this sequentially is quite easy. So you take a vector and you put the result in a second vector by doing this computation element by element. And once you finish, you substitute, you swap, and you continue the computation. Okay? Doing that in parallel means that every task works on one element. They start by computing the formula, and then they wait for everybody to finish so that we can swap the vector and continue. Okay? So we want to implement this, but before implementing this, we need a synchronization mechanism. We want to have 8 threads that are blocked and waiting for the start. And when I start, all of them start executing their computation, and then they block again, waiting for the next round. And of course, I should be informed when they wake up. Sorry, when they block again, so that I can take the result, do the swap, and continue. So let's see if we can implement this synchronization class. So I call this, with a lot of fantasy, synchronization barrier. And I'm going to use a mutex. And I'm going to use a condition variable. So I'm using also 2 variables, max threads and number of blocked threads. And of course, I'm going to initialize this with the maximum number of threads I want in my I want to control. Then I need to, of course, for all threads to synchronize. So I'm going to provide a function that I call sync. So basically every thread will synchronize by calling sync. And I'm going to provide a function start that I call when I want to start all threads that are blocked. Just 1 second. I have to do 1 second break. Okay, and then last thing we need to do is, okay, let's do a start first, and then we see what we need else. So sync is called by the thread for synchronizing, for saying, okay, I finished my job, and now I wait for the next start. And the start is called by the thread manager, the one that controls the other thread, for saying, okay, now we are ready for the next step. So everybody start, okay? And last function is going to be wait, where the manager waits for all of them to finish. Okay, so let's start writing this function. By the way, of course, we need to disable copy constructor and the assignment operator. So for not losing too much time, I'm going to skip this. So, as always, let's take the lock on the mutex. Then I want to synchronize, so I have to stop, right? Because I finished my job. So I want to wait for the next start. So I'm going to stop anyway, right? But before that, I have to increase the number of blocked threads. So I'm signaling everybody that I'm blocking, and then I wait for the other threads to also reach this point. Okay? Now the start. The start basically is a sort of notify all, because I need to wake up everybody. So what I do is I put n blocked to 0. Nobody's blocked anymore from what concerns me. And then I'm going to notify all. So all blocked threads are unblocked. And then basically I finish. And the last thing I'm going to do is the wait. So for the wait, I'm the manager. I actually should wait on a different condition variable, because if I use the same condition variable, that's not very clear what is going to happen. So this is the condition variable where the threads are blocked, and I use this as the condition variable for the manager. So who is going to notify this condition variable? So suppose, for example, the threads are executing. I do a wait as a manager because n blocked is less than a max thread. I'm going to be blocked here. So who is going to unblock me? Well, of course, the last thread that's synchronized. So if I'm the last one, I notify the manager and then I wait. The manager wakes up and it finds that n blocked is equal to max thread, and so basically wakes up from here. Okay? What if I call start when I should not, as an error? Well, just to be sure, I could actually call wait before calling start. Okay? So I call wait, and then I call start. So the start is actually always preceded by a wait. Or I can call wait, and then inside start, the wait, of course, will not block. So this is not the most efficient way to implement, but in a concurrent programming, the first time we implement some mechanism is always better to try to stay safe and to stay clean. So I'm not caring about optimization right now. I'm just caring about correctness. So let's see. Maybe I'm doing some errors, so let's check together. So sync is called by the threads that want to synchronize with on the barrier. Increments n blocked. If n blocked is equal to max thread, I'm going to modify the manager, and then I wait till we wake up later on. Manager usually calls starts, waiting for all threads to synchronize. When all threads are synchronized, he will call start later on for notifying all threads and start again. Okay? So now we do an error. Sorry. Now we do an example of threads. So I'm going to write threads that synchronize all together in a certain order. So I'm receiving a sync barrier as a parameter, and I'm going to do a for cycle. So all threads initially synchronize on the synchronization barrier. Then they do a for cycle in which they print something and they synchronize. They print something and they synchronize, and so on. Okay? And then in the main, I'm going to create a synchronization barrier with 5 threads. I'm going to create 5 threads. Okay, so I created the 5 threads, and then after I create the 5 threads, I have to start 10 times, actually 11 times, right? And then wait for the termination. So the start will wait and then start, wait and then start. And so actually I should be able to Okay, should be over now. Let's see how many errors I did. So this is called thread group. So let's see. Max thread, maybe it's max threads. Never remember the name of the variables. Yes, it's max threads. Okay, so that's the first error. Transform not declared in this scope because it's in algorithm. Okay, let's hope that I did not do any error. Yes, it should work. So basically, they do their computation step by step. Let's see. Yes, so basically there is a thread 0, step 0 for everybody, then step 1 for everybody, then step 2 for everybody, then step 3 for everybody, okay, and so on. So it goes step by step. If we remove the synchronization, for example here, then we run into trouble because the steps should be mixed up in a random way. Yeah, as you can see, thread 5 executes step 1, 2, 3, 4, 5, 6, 7, 8, 9 all together. So instead of every step all thread execute together, every thread executes all step one after the other. So the synchronization in this case is not there. If we go back to our previous implementation, okay, the printing is what is it, but you can see that, for example, all 5 thread executes the 7th step together in random order, of course, of printing, but nobody executes step 8 before finishing step 7. Okay, so that's it for today. And tomorrow we'll continue a little bit by implementing some parallel algorithm. For example, the one I described here. And we will reason a little bit also on other ways of parallelizing code. For example, by using asynchronous function calls, promise and futures. Okay? So that's it for today. Thank you. If you have questions.
Professor, can we ask a question about the assignment?
Yes.
One second. I was having a question about the collision of the nodes. If we use for the wireless protocol the same protocol as the Ethernet, like the how it's called, we
Yes,
are,
carrier sense and collision detect.
yeah, exactly, with the how it's called, the contention window of a period. If we use inside the range that way
Yes.
to implement the
Yes,
collision,
yes.
we should avoid every type of collision inside the range, right?
Well, in abstract, yes. In practice, not necessarily, because um, uh, it may happen that two nodes both listen and both decide to start sending at the same time. Yeah, so basically, if you remember well, Ethernet has a backoff period, which is a random number, right?
Yes.
And this is for avoiding the situation in which everybody is listening. One is transmitting and everybody is listening.
Okay.
When that one is finishing transmitting, of course, the other ones would like to transmit. So the probability that both choose the same interval of backoff is quite low, and so this should reduce the number of collisions. However, it's not impossible that two nodes exactly extract exactly the same random number and start transmitting at exactly the same time.
Okay.
So physically, there is always a small interval between the time in which I'm sensing and the time in which I start transmitting. And if this interval is I mean, the same for two nodes. It can happen that they start transmitting at the same time.
Because they would find the channel free at the same time, basically.
Yes, they will find the channel free at the same time, and they start transmitting exactly at the same time. So there is a small probability, but nevertheless, this is not null. It's not zero.
Okay, I got it. And the other problem of collision, of course, is the hidden problem already.
Yes, they even know the problem, of course.
The hidden non problem. Okay. Thank you very much.
Okay. Other questions? No? Okay. So if you have other questions, you can ask at any time, even by email. Hmm? No, sorry for I'm a little bit late for correcting the second projects. Hopefully this weekend I will actually do it and finish. Okay, so probably next week you will receive the result of the second project. Okay, bye bye.
Bye.